my name is Jacqueline, and today I'm going to talk about the chapter 18, Heat and the First Law of Thermodynamics. And the first topic we're going to discuss is the definition of heat. And this topic talks about a system and the thermal energy. But first of all, what is a system? Well, a system is an object or a collection of objects that we want to examine. And if we look at these drawings, the water in each glass is a different system with a certain temperature, which is called Ts. And the area of a place, which are represented with these little dots, is an environment with a temperature, which is called Ta. And if we, well, hypothetically speaking, if the temperature of the system is different than the temperature of the environment, then the temperature of the system is going to change until it reaches or until it's equal to the temperature of the environment. But what is the difference between the system and the environment? Well, there's just one thing, that the environment is large compared to the system. And now, thermal energy. Thermal energy is the change in temperature of the system due to the transfer of energy between a system and its surroundings. And when there is a transfer of energy between one body to another, it is called heat. And this is symbolized by the capital letter Q. And again, by looking at this drawing, when in the first glass, when the environment is transferring energy to a system, or when the system is gaining energy, that means that the temperature of the environment is going to be higher than the temperature of the system, and therefore the heat or the thermal energy is going to be larger than zero. Also, when the on the other side, when the temperature, when the environment is absorbing energy from the system, or the system is transferring energy to its environment, the temperature of the environment is going to be lower than the temperature in the system. Therefore, Q, or the heat, is going to be lower than zero. But when the temperature is the same in both, that means the environment and the system have the same temperature, then the thermal energy is going to be equal to zero. So now we're going to talk about the second topic of chapter 18, which is called mechanical equivalent of heat. And first of all, we're going to begin with the definition of a calorie. And a calorie is the amount of heat required to raise the temperature of water. Sorry. So now we're going to talk about the second topic of chapter 18, which is called the mechanical equivalent of heat. And first of all, we're going to begin with defining what a calorie is. And a calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 Celsius. And another common way to measure the heat is the British thermal unit, or BTU, which is the amount of heat required to raise the temperature of 1 pound of water by 1 Fahrenheit. And now, however, the change in temperature of water is a function of the amount of energy required. Okay. So now we're going to talk about the second topic of chapter 18, which is called the mechanical equivalent of heat. And first of all, we're going to begin with the definition of a calorie. Well, a calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 Celsius. And another common way to measure the heat is the British thermal unit, or BTU, which is the amount of heat required to raise the temperature of 1 pound by 1 Fahrenheit. However, the change in temperature of water is a function of the amount of thermal energy transferred to it, depends on the original temperature of water. And on the other side, in 1843, an English physicist called James Prescott Joule show with the help of this little machine that the mechanical energy could be converted or transformed into thermal energy, and therefore he obtained a relationship between the calorie and the joule. And since there, a calorie is an established value and is 4.186 joules, and this is in honor of his name. So now I'm going to explain to you the third topic, which is called heat and work. And by looking at this drawing, here we have a gas-filled cylinder with a piston in which the gas is in thermal contact with an infinite thermal reservoir. And if we look at the drawing here, we can see that an external force pushes on the piston, and that causes an increase in the pressure in the gas. So when that external force is removed, and that allows the gas to push out the piston. Sorry. So the gas push out the piston a distance called the R. So that means that the work done by the system in this process is given by this equation, which is the first one. And in order to explain the behavior of this system, we have to take into account two things. The first thing is an initial state given by the pressure 1, the volume 1, and the temperature 1. And the second thing is that we have to take into account a final state, which is the final pressure, volume, and temperature. So during this process, when the thermal energy is transferred into the system, we are talking about a positive heat. And when this thermal energy is being transferred out of the system, we're talking about a negative heat. And since, as I already mentioned, this is a thermodynamic process, because a thermodynamic process is when you have a progression from an initial state to a final one. So since here we have an example, we're going to we can establish that the work done by the system is given by this second formula. Finally, we're going to talk about one of the main topics in chapter 18. Finally, we're going to talk about one of the main topics in chapter 18, which is topic number 4, first law of thermodynamics. And first of all, let me explain you the different thermodynamic systems. Because we have three: an open system, a closed system, and an isolated system. So first, an open system can exchange heat, energy, and mass with its surroundings. And on the other hand, a closed system is a system into or out of which thermal energy can be transferred, from which no constituents can escape, and to which no constituents are added. And finally, an isolated system, as the word isolated, is a system that has no interactions or exchanges of constituents with its surroundings. So now we can establish that the change in the internal energy of a closed system in terms of heat and work is given by the following formula, which is this one. And this is known as the first law of thermodynamics. And well, basically what this established is that the change in the internal energy of a closed system is equal to the heat acquired by the system minus the work done by the system. In other words, no energy is lost. So basically we're talking about the conservation of energy, because even though heat and work can be transformed into thermal energy, no energy is lost. Now we're going to discuss the topic number 5, which is first law for special processes. And in this topic we're going to talk about 6 special processes which can be described by the first law of thermodynamics, which is given by this following formula. So we have to pay attention to that formula. So first we're going to talk about the adiabatic processes, and those take place when no heat flows when the state of the system changes. And an example of it is when the process occurs so quickly that there is not enough time for heat to be exchanged. So that means that heat is going to be zero, and therefore the change in the internal energy is going to be equal to minus the work done by the system. So now, a constant volume process can also be called isochoric processes. And in these kind of processes, there is no work done by the system, and therefore the internal energy of the system is going to be equal to the heat absorbed by the system. And an example of this process is when is cooking food in a pressure cooker. Now, a closed path process is when a system returns to the state at which it started. So that means that the change in the internal energy is going to be equal to zero, and therefore the work done by the system is going to be equal to the heat absorbed into the system. So now, a free expansion. So here for this process, imagine that you have a container for a gas, and suddenly the container expands in size. So that means that the gas will fill the whole volume. Therefore, during this process, there is no work done, and there is no heat absorbed. So that means that the change in internal energy is going to be equal to zero. Now, when you have a constant pressure process, those are also called isobaric processes. And during these processes, the volume can change. So that allows the system to do some work. And also, the pressure remains constant. So that means that the change in internal energy is going to be equal to the heat minus the pressure times the change in the volume. So finally, for constant temperature processes, these are also called isothermal processes. And here, heat can be exchanged in order to maintain a constant temperature. So now I'm going to talk about the topic number 6 from chapter 18, which is called the specific heat of solids and fluids. And here we have three main topics, which are the heat capacity, the specific heat, and calorimetry. So first of all, let me explain you what heat capacity is. And it is represented by the capital letter C. And actually is the proportionality between the temperature changes and the heat of an object, and is represented by this formula. And it's basically the heat required to raise the temperature of the object by a given amount, and its units are joules per Kelvin. So now, in a specific heat, which is represented by the lowercase c, is given, is defined by the heat capacity per unit mass. So in terms of the change in temperature and heat, is given by this formula, and its units are joules over kilograms times Kelvin. And since it is defined in terms of the temperature, you can also use Celsius instead of Kelvin, but it's basically the same thing. So for calorimetry, this is mainly a topic about chemistry, so I'm just going to explain you what a calorimeter is, which is a device used to study the internal energy changes by the thermal energy transfer. Hope you're still there because we're almost finished. We're in chapter 7, which is called the latent heat and phase transitions. So first, let me talk to you about the phase changes, because during the phase changes, the temperature remains constant, and when the heat that is required to melt a solid divided by its mass is called the latent heat of fusion, or L fusion. And when the heat that is required to vaporize a liquid divided by its mass, it's called the latent heat of evaporation, or evaporation. And also, the temperature that it's needed to change a solid from a solid to a liquid, it's called the melting point. And the temperature that is needed to change from a liquid to a gas, It's called the boiling point. And well, this the first equation we have here is just like when you have to convert when you're melting an object, which means that you are changing the substance from solid to a liquid. And the second one refers to the when you're vaporizing an object, or well, sorry, not an object, a liquid, which is when you change the substance from a liquid to a gas. And this is the formula you use. So it's the units of the latent heat are joules per kilograms, and calories is also used. It's common actually, and it's given by its units are calories over grams. So now I'm going to talk to you about the phase transition temperatures in elements. And when there is a crazy element that it's solid, that its state of matter is solid, and it converts into a gas, that process is called sublimation. And when you heat that gas, its free electrons or its electrons are going to form another state of matter, which is called plasma. Finally, we're on the last topic of chapter 13, which is modes of thermal energy transfer. Woo! So, we have three modes here are the main modes of thermal energy transfer, which are radiation, convection, and conduction. And I'm going to explain them with the help of this drawing, which is actually a campfire, in case you were wondering. And first of all, let me define what radiation is. Well, radiation is the transfer of energy via electromagnetic waves. And by looking at this drawing, and if you have been near a campfire, when you sit near the campfire, you feel the heat radiating like these two people. And convection is related to the movement of a substance from thermal contact with one system to thermal contact with another system. And it's represented, it rises in the form of the flame and the hot air above the flame, this part. And finally, which is I think the most important mode, because it's the mode that we have discussed in class, which is conduction. Involves the transfer of thermal energy within an object, or the transfer of heat between two or more objects, and which are in thermal contact. And here we have two new concepts for this mode, which are the thermal conductivity, which is represented with the letter K, and these are its units. And finally, the thermal resistance, which is represented with the letter R, and these are its units. Thank you for watching. Hope to see you next time.